3. A bicyclist travels 450 meters in 20 seconds. So that's 450 meters in 20 seconds. What is it in kilometers per hour? So I'll start with the meters. Need the meters to go, so that one's in the numerator, so I have to put it in the denominator. And I need kilometers. And kilo means 1,000 meters, so I have 1,000 meters is 1 kilometer. That would get it into kilometers. Now I got to get hours. The seconds are in the denominator, so now I have to put seconds in the numerator. I'll go to minutes first, and 60 seconds is 1 minute. But I need to get hours, so I'm going to put minutes in the numerator to cancel those minutes, just like those seconds cancel. And then I need hours, and I know 60 minutes make 1 hour. So, doing the math, I have 450 times 1 times 60 times 60 for my numerator, which is 162 and 4 zeros, divided by, and then I got 20 times 1,000 times 1 times 1, so that's 20,000. And so I got to divide these two, and this would be kilometers left and hours. So I get this divided by 20,000, and I get 81 kilometers per hour. Okay. A bicyclist is burning 300 capital calories per hour. What's the power output in watts? Now, a watt is joules per second. And some of you know that there's 4,190 joules is 1 capital calorie, or you could take 4.19 joules, makes it 1 small calorie. So you can convert capital calorie to small calories, which is 1,000 times more. So this would be 300,000, or you can just use this. I'll just use this, and so capital calorie is 4,190 joules. So then we'd have joules per hour, but we need joules per second, so we need the hours to disappear. So that'll have to go in the numerator to be able to cancel that. I'll go to minutes, and 1 hour is 60 minutes. And then we go to seconds, so I need the minutes to cancel and get seconds, and 60 seconds is 1 minute. So we get in the numerator 300 times that, and the denominator 60 times 60. So on 300 times 4190 is 1257000, divided 60 times 60 is 3600, and this would be, see, the minutes are gone, we have seconds, joules per second. So this is watts, because a joule per second is a watt, so we just got to figure out what that is. So I'm going to divide by 3600, and I get 349 approximately watts, joules per second. Okay, this one. So we have, I'm going to do this on this side, 19 minus 9, parenthesis, 5 minus 2 plus 6, close parenthesis, minus 8. Inside the parenthesis, I have subtraction and addition. And they're the same level, so you do them left to right. So 5 minus 2 is 3. 3 plus 6 is 9. And this is times, and this is 19 minus 8. So even though 19 minus 9 is tempting, we have to do the multiplication first, so we get 19 minus 81 minus 8. And now we have subtraction, they're the same level, so we subtract left to right. So 19 minus 81 is negative 62 minus 8. They're both negative, so they're actually going to add, and we get minus 70. That's A. B, 1/2 divided by 2/3 minus 1/4. Okay, 2/3 minus 1/4. When you add or subtract, we need a common denominator. 3 and 4 both go into not 6, but 12. To make this be a 12, I need to multiply the denominator by 4 and the numerator by 4. To make this be 12, I have to multiply by 3 and 3. So I have 1/2 divided by 8/12 minus 3/12. So that's 1/2 divided by 8/12 minus 3/12 is 5/12. And when you divide fractions, it really means half divided by 5 and times 12. So let's just turn it over. So we're doing that. 1/2 times 12/5, which is 12 over 10. When you multiply fractions, you multiply straight across. And that reduces, if you wanted, you don't have to, that reduces to 6/5. Some people wrote that as 1.2. Either of those answers are fine, or 1 1/5 would be fine. Number 5. So we have 0.00034 kilograms, and kilograms, we're headed towards milligrams, so we have to go to grams first, and there's 1,000 grams in a kilogram. Kilo means 1,000 grams, so it takes 1,000 grams to make 1 kilogram. And then we need, that would get the kilograms to cancel, but we're in grams, now we need milligrams, and that means 1,000th. And so we want the grams to cancel, and we want milligrams, and that means 1,000th of a gram, so it takes 1,000 of these to make 1 gram. So I'm multiplying this by 1,000, and then by 1,000. And dividing by 1, which doesn't do anything here, and that would cancel the grams. So 1,000 times a number just moves the decimal 3 places, so that these two multiplied would be 0.34, times 1,000 again would move it 3 more places and make 340 milligrams. Page 2, number 6. 4% of the mass of a beverage is alcohol. That means 4 parts out of 100, or 0.04. That means 4% of the mass of the drink. The person has an estimated 3 liters of blood and 250 milligrams of the beverage. So they drink 250 grams. That's a cup of 4% alcohol. So it's a cup of wine or a cup of beer or whatever. But not all of this is alcohol, only 4%. So we take it times 0.04 to find out how many grams that is of alcohol that goes into their blood after the hour that it says, 0.04 times 250, and we get 10 grams. So now blood alcohol is how many grams? Well, there's 10 of them in the blood after the hour. And the amount of blood is, where did it say that? 3 liters. But we need it in milliliters, so we need liters to cancel. And we need milliliters, that's 1,000th of a liter. So we need 1,000 milliliters to make 1 liter. So now we'd have grams per milliliter, and that turns out to be 10 divided by 3,000, which is 0.0033 repeating grams per milliliter. But blood alcohol is done in grams per 100 milliliters, so we know how to make this be 100 down here instead of 1. So we multiply the numerator by 100 and the denominator by 100 to make it 100 milliliters. And we get 100 times this would move the decimal 2 places, and we get 0.33 grams per 100 milliliters. So the blood alcohol content rating on this one would be 0.33. Okay, Antarctica, a big continent that had not regular shape, but the amount of area it has is 14 million kilometers squared. So if you made it into a rectangle, it would be something by something that multiplied comes out to be 14 million, approximately. And it is 2.15 kilometers thick. And to find the volume of this, you take the area times how thick, and so we take it times this number times 2.15 kilometers, which works out to be 14,000 million times 2.15, and we get 30,100,000. So we get 30 million kilometers times kilometers times kilometers, kilometers cubed. Now that's how much ice it is. But when ice melts, it becomes 5/6 of what it really was. It actually shrinks. There's not that much volume of water. So we have to take the 30,100,000 kilometers cubed times 5 divided by 6. So if I multiply this by 5 and then divide by 6, I get 2508333, roughly 25 million kilometers cubed of water. This was of ice. And this is the water. Okay, on this one, you catch a glimpse of from an aircraft of some sort of refugees herded onto a soccer field. Now, a soccer field is roughly the size of a football field. You can use whatever you want to estimate for it, but a football field is 100 yards or 100 meters, either one's reasonable, and the width is more than half the length, so I would say 50 or 60 yards. But if you use something else, so these are assumptions. That I'm making. The size is this. The other assumption I'm making is how much area does a person take? Well, I think maybe 2 feet by 2 feet, maybe 3 feet by 3 feet, but whatever, so that'd be 4 feet squared. So what I should do is figure out how many square feet there is and divide it by 4, if this is my assumption. So here's my one assumption, here's my other assumption. Okay, so I got 2 assumptions. Now, if I have 100 yards, if I multiply it by 3 feet makes 1 yard, I'll have 300 feet, and I'll have to do the same here. 3 feet is 1 yard, so I'd have 180 feet, so I have 300 feet times 180 feet, and times, or divided by, well, actually I'll write it this way. One person is 4 feet squared. I want the feet squared to cancel, so feet squared. 4 feet squared is 1 person. So the feet squared cancel. So I'll have 300 times 180 divided by 4. So my estimate is 300 times 180 divided by 4. And I get 13,500 people, refugees, fitting on a soccer field. That's a lot of people. That's like the entire town of Ellensburg's on that. Okay, last one, problem-solving techniques. Okay, so we did, like on the problem like this, we did a couple problem-solving techniques. We did this one, and we did in class. We guessed and checked, and we also looked for patterns. Guess and check and adjust. So here's this. I would explain somehow. That's what we did here, and maybe explain a little bit about that, describe the technique. We looked for patterns. so that we could predict, so we could make a prediction. We on so you would explain that. On the hat problem, the prisoners with the hats, we made a list / table of all possibilities, and then did some elimination. On the pennies on the table, or on the one where we were jumping the colors, we simplified it to simplify the problem, and then we again, with the simplified, we look for understanding, and maybe even patterns, and so that we could then get to the answer. So we simplified the problem. On the duck and wolf and goose and mouse and whatever, taking the canoe back and forth, you could make a model and then try to move it by using the model. So experiment and make a model, for understanding and experimenting. Okay. We can make 6. Draw diagrams or pictures to aid in understanding. And then some of you had some other things like think about other possibilities, think out of the box. Take a break from the problem and come back to it is another problem-solving technique. So there's 3 more that I gave you. So that's 9 that we've had, and I've only asked you to do 3. Now on the retest, I might ask you to do more, just because I want to see if you can do them. Okay, so that's my video of the test.